Yes. Dear students, good afternoon. Welcome to SE Engineering College GATE coaching class. I am Dr.N.MAGADEVI, Associate Professor, Department of Electrical and Electronics Engineering. Today we are going to discuss about the topic distribution systems for electrical engineering. I hope all of you applied for GATE 2026. It is going to, the exams will be on February month and the results will be published in the month of March. This is the electrical engineering GATE coaching, GATE syllabus. In this we are going to see about only the distribution systems. In this the important topic is single line diagram. So we have to start it from the single line diagram. It is simply a GTD, that is generation, transmission and distribution. So this is for generating station. So this generating station we will generate the electrical voltage. It will be around 11 kV we will generate, and this sinusoidal sign represents it is a alternating current. That is, we are not generating a direct current, we will generate only the alternating current. So this generating station, for example, we can take the thermal power station in ETPS or otherwise nuclear power station in Kalpakkam. Like that we are having idle power plant, wind power plant, all the things. So in the power stations they will generate 11 kV mostly. After that in the generating station itself it will be stepped up into 220 kilovolt. So this portion will be in the generating station. After that, this is your generation, that is your first one, and the next one is transmission. So once the voltage generated, once the power is generated, it will be transmitted to the consumer. So here we are having so many number of stages, that is, we will have the primary distribution, secondary distribution, and we will have the primary transmission, secondary transmission, and also in between the generating station and the consumers you will have so many number of substations also, because we are going to transmit the voltage for long distance. So if you are traveling, if the voltages or power is traveling for long distance, means there will be so much of voltage drop because we are far away from the generating station. So for that what we are doing means we are using the substations. So in the substations we may step up the voltage or step down the voltage. So if there will be 4 substations in between the generating station and the consumer. The 4 substations, it may step up the voltage or step down the voltage, and also in sometimes we will have the equal ratio transformers, or otherwise we can change the frequencies also based on the applications. The first substation will be in the generating station itself. So why we are using the transformer here means, in the substation this the transformer is the main thing. Beyond that we will have the circuit breakers, isolators, and then bus bars. So many productive devices will be there. So our ultimate concentration is on the active parameter, that is the voltage and current. So that only we are talking about here transformer. So other productive device will also be in the substation. So in the substation we will have the transformer. That transformer is a step up transformer. So what the step up transformer will do, it will step up the voltage from 11 kV to 220 kV. So if you are this is a symbol for a transformer. So if this portion is called as primary winding and this is where secondary winding. In between the primary winding and secondary winding we will have the iron core. Why we are using the primary winding means, it is an inductor only. That is, primary winding is nothing but in the transformer how they will manufacture means, first they will take the former. So that former will be just like a bobbin, just like your tailoring machine, and in the bobbin first you do the insulation tape, hessian tape, like that. After that we have to calculate the number of turns in the primary winding and number of turns in the secondary winding. Based on the voltage we have to do the calculation. The calculations are there based on the voltage, based on the current carrying capacity. So we have to calculate the number of windings in the primary and the secondary coil. So based on that, first you have to take the bobbin and you have to wind the hessian tape, that is a insulation tape. After that we have to take the wire, conducting wire. Mostly it will be made up of copper, and we will start the winding. First one is for example I am taking the primary winding for 40 number of turns. That starting will be in the outside and we will wind the 40 turns. So on the ending we have to take it outside. So these are the 2 terminals here. Primary winding, 2 terminals will be there. And for that only we will apply the voltage of 11 kV. Next portion is where iron core. So there are various types we can use. Here we are using the iron core transformer. Air core transformer is also there. Why we are going for iron core transformer means first we have taken the bobbin and we have given the insulation, and next we mount the primary winding. After that we have to do the insulation again, because there is no physical connection between the primary winding and the secondary winding. Primary winding and the secondary winding must be isolated, and you have to do the SN tape for that. After that we have to use the iron core. So what is the iron core? Iron core air core transformer is also there. So if you are using the iron core means, if you are giving the voltage of 11 kV to the primary winding, there will be a flow of flux in the coil, and that flux has to link with the secondary coil also. That is, it is physically separated but magnetically coupled. The primary winding and secondary windings are physically separated but magnetically coupled. The part is that if you are giving the voltage to the primary winding, current will be flowing to the coil. It will be flow to the primary winding coil, and it will produce the flux. Why the fluxes are produced means, if there is any charge, if it is stationary, there will be electric field around the charge. That charge may be a proton, electron, neutron, we can take it, but mainly we will concentrate on the electrons only, because it is a negatively charged particles. If there is a flow of current means, it is nothing but flow of electrons. So when the electrons are moving from one part to another point means, there will be a magnetic field around that portion. So that it will produce a magnetic field. So for that only, current is nothing but I is equals to dq by dt, that is rate of flow. Whenever you are seeing d by dt means, it is nothing but rate of change with respect to the time, and that q is nothing but the charge. It represents the charge. Here we are taking mainly the electrons. So if there is a flow of charge means, there will be a flow of current, and around that we will have the magnetic field. So magnetic field means, what are the main parameters? There will be a magnetic flux, there will be a magnetic flux density, there will be a magnetic field intensity. What is a magnetic flux? Flux is nothing but the imaginary lines. So if you are having a light means, light rays will be coming outside, we cannot able to see, but we are getting the light energy. Similarly, wind, we cannot able to see the wind, but there is a wind flow will be there. So like that, if there is a flow of current means, there will be a magnetic flux around that core, around that coil. So that magnetic flux lines, how it will be means, it will form a closed path, like a circle or any other shape, but it has to form a closed path. So it will form, for example, if you are taking a iron bar, and if you are winding the coil and you are giving the alternating current, what it will do, the current will be flowing, and there will be a magnetic flux. What we will represent this in this north and this portion is south pole, like that only we will represent, but it is not the actual case. There will be a flow of flux like that, that is, it will originate from north pole and it has to terminate from the south pole. That is, if the flux lines are coming from one end means, we will representing it as a north pole, and if it is terminating, that is it, if it is flowing inside the core means, we will represent it as a south pole. But there is a closed path for the, that is it will form a closed path, that is a magnetic flux will flow in a closed path, that is the magnetic flux. It is represented by the letter phi, and the unit is Webers. We will represent it as WB. And the second one is magnetic flux density. So what is a magnetic flux density means, if you are having a so much of charge means, there will be so much of magnetic flux will be there, and the density will be maximum. So what is the density you will represent? You have to consider a surface. So if you are considering a surface means, what is the number of lines passing through the surface divided by the area will give the density. So flux density means flux by area, current density means current by area. So these are the general things. So there will be a flux density, it will be represented by the letter B, and the unit is Weber per meter square, that is flux density is flux by area, Weber per meter square. And the third one is magnetic field intensity. So intensity is a important thing. So if you are having more charges, the intensity will be maximum. So at a particular point we have to say the intensity. So if you are taking a density means, you have to consider a area, but if it is a intensity means, you have to take a particular point, that is one dimensional. So in that point what is the intensity because of that current flowing. It is called as magnetic field intensity. H is equal to Ni by L, that is mmf by length. So that is the three main parameters. So what are the three main parameters? Magnetic flux density, magnetic field intensity. So where it is produced, if you are giving 11 kV to the primary coil of the transformer, it will produce the magnetic flux. Okay. Next one is we are having the iron core. So what is the use of iron core? If the fluxes are flowing means if there is a path for the flux, the intensity will be maximum. So if you are not providing the flux means it will be spread out. So the density will be reduced, the intensity will be reduced. So in order to avoid that one, what we are doing means we are using the iron core. That is, we are taken a bobbin, we wound the primary coils, after that we put the insulation. Again, next what you have to do, that bobbin, next we have to bind the secondary winding, again we have to put the SI tape because it has to be physically separated. And the next thing what you have to do means you have to insert the iron core. So that iron core may be of I type or E type, so many types are there. So if this is a bobbin, you have to insert this. If this is a hole means you have to insert the E core here, and opposite you have to insert the E core I, but here he will be having some gap. So in that you have to fill the I core. So now it will form a transformer. Okay, why we are going for the iron core? Why it is necessity means, so for the flow of flux we are providing the path. So the epsilon R value is important. So what is the epsilon? Epsilon is the permittivity of the media. So if the fluxes are produced, it has to flow through some surface. In that surface, what is the media is present? It is important. So if you are having a permittivity, so permeability or permittivity, you know very well, permeability is for the magnetic field and the permittivity is for the electric field. What is the permeability here? Because it is a magnetic field only. What is the permeability? Permeability is nothing but ability which allows the magnetic flux to pass through it. So that permittivity plays a major role in the magnetic field. So what we have to do means, to avoid the leakage fluxes, we have to form a path. How to avoid the leakage flux means we have to provide the path which is having the highest permittivity, that is permeability. Highest permeability material we have to select. So for that only we are taking the iron core. Iron is having more epsilon R value. Actually the permeability we will have in the formula mu is equal to mu naught into mu r. Mu naught is the absolute permeability, mu r is the relative permeability. So mu is the permeability. So permeability is nothing but the ability of the media to pass the magnetic flux through it. It is the permeability. So mu naught is constant, 4 pi into 10 power minus 7. But mu r, based on the material, it will be varied. If you are taking a free space means the mu r value is 1. If you are taking the iron core means it may be 3, 4 based on the alloy we are using. So it will be varying, but it will be greater than 1. So that only we are using the iron core. So now E and I core cannot be represented. So the symbol we are using is just 2 lines we have to represent. This represents the iron core. So it will avoid the leakage flux. So air core transformer also we can use based on the applications. We have to select the transformer. So first you have to wound the primary winding, and we are given the 11 kV voltage to the primary of the transformer, and it will produce the magnetic flux. That magnetic flux now link with your secondary winding. So how the transformer is manufactured? You have to take a bobbin, first wind the SI tape, next wind the primary coil, take the 2 leads outside, apply the voltage 11 kV from the generating station, and next you have to put the SI tape again, and you have to wind the secondary number of coils for so many number of turns, and you have to take the 2 coils outside. This is where output of your transformer. So now how we are selecting means here we are using a step-up transformer. So what is a step-up transformer? The input voltage is 11 kV means the output voltage is for this particular substation we are using 220 kV. So if you are giving 11 kV input means we will get the 220 kV. It will be stepped up. For that we are having the relations. That is where we are having the transformation ratio K. K is equal to V2 by V1, which is equal to I1 by I2, which is equal to N2 by N1. So if you want more voltage means you have to use the more windings. It may be on primary side or secondary side. So primary side the number of turns is less when compared with the secondary winding. That is the reason. Now the voltage has been stepped up in the generating station itself. This is our first substation. After that we have to transmit. This portion is generation. This up to this portion is, it is called as transmission. After that, here there is a distribution and here there is a distribution. Okay, so that is what GTD represents. Now the generated voltage given to the step-up transformer 11 kV will be converted into 220 kV. It will be transmitted. This transmission is called as primary transmission. For the primary transmission, we will use the wires only, but it is called as a feeder. So feeder is a conductor from which we cannot able to drop the voltage. So this is the main important thing, because if you are dropping the voltage here means automatically the consumer will not get the required voltage. It will be reduced again. So for that we will use the feeders. So feeders are designed based on the current carrying capacity, not on the voltage, because we are using the conductors only, but the voltages are not tapped off. So the feeder are designed based on the current only, not on the voltage. So feeder is a conductor from which the voltage cannot be tapped off. So it is called this portion from this substation to this substation, it is called as primary transmission. So the high voltage will be transmitted through the wires here and it will reach the receiving station. This substation is called as receiving station. So in the receiving station, if you are seeing the symbol itself, it is a step down transformer. That is, primary number of turns is maximum, secondary number of turns is minimum. So it is a step down transformer. The voltage is stepped down to 33 kV. In this particular substation, it is 33 kV. So the input voltage will be 220 kV, output voltage will be 33 kV. After that, it will be again given to the feeders. This transmission is called as secondary transmission and this substation is called as substation alone. That's all. And here also you are using a step down transformer, because primary number of turns is more when compared to the secondary number of turns. And this 33 kV input will be converted into 6.6 kV or 3 kV, or based on the application it will be stepped down. And then this voltage will be distributed here for a bulk consumers. So in some companies, factories and all, they are in need of more voltages, high voltages they will use. Inside that they will use the indoor substations. There they will step down the voltage, or directly they may use the high voltage for some machines and all. So it will be given to the bulk consumers. So this portion is called as primary distribution. This portion is called as primary distribution. After that, it will be given to the feeders. This is where primary distribution, it will be given to the conductors and it will reach where distribution substation. In the distribution substation, again the voltage will be stepped down to 440 volts or 230 volts based on the single phase or three phase supply. So 440 means we will use it for three phase supply and 230 for single phase supply. Most probably nowadays we are using three phase supply only, 440 volts. It will be again stepped down and here it will be distributed to so many number of consumers via the distributors. It is called as secondary distribution, and here we will use the service mains. Service main is nothing but from which we are taking the connection to the house. So the three main conductors are feeder, distributor and service main. Feeder, it will be based on the current carrying capacity, and then distributor, it will be designed based on the voltage, because we are tapping so many number of voltages, so it is based on your voltage. And then the service main, it is nothing but from which we are taking the connection. These are the main things. So this is where single line diagram for generation, transmission and then distribution. So the distribution is where comes here only the distribution, secondary distribution. Here the distribution is primary distribution. That is our topic, distribution systems. So that's all about the distribution systems. Next we will see the classification of distribution systems. How the distribution systems are classified. The first one is based on the scheme of connection, how we are connecting. That is, if you are having a distributor mains, you may use a radial distributor, that is just like a line, it is called as radial distribution, or others you may form a circular conductor also, it is called as ring main distribution. So if you are taking a radial distributor means the voltage may be fed at one end, or the voltage may be fed at both the ends, or the voltage may be fed at the center. There are three categories. And the next one is ring main distributor. So ring main distributor means it has to form a closed path with the interconnection and then without interconnection. There are two types. And the next one is based on the distribution. which media we are using. We may use the overhead lines or underground cables, that is OHL and then UGC. So we can use the overhead lines or otherwise we can use the underground cables. We can distribute the voltages. And the next one is based on the supply. We may use AC supply or we may use the DC supply also. AC distribution, DC distributions. And the next one is nature of the load. Nature of the load, concentrated load, uniform load, or both the loads at a time we can use. That is concentrated load means at a particular the current value may be varied and the distance may be varied. But if it is a uniform loading means at regular interval of time you have to take the same current only. It is called as uniform loading. Some application you may use both the loadings also. These are the main categories. That is based on the connection, distribution, based on the scheme of connection. It may be a radial distributor or ring main distributor, or based on the voltage it may be AC voltage or DC voltage, and then method of distribution OHL or otherwise UGC, and then nature of the load, concentrated load or distributed loads, uniform loading or concentrated loading. Let us see one by one. The first one is DC distributor fed at one end for the concentrated loading. That is DC distributor. That is DC distributor fed at one end concentrated loading. It may be overhead line or underground cables. Here we are taking the overhead line for our understanding. So this is a DC distributor. AB is a DC distributor. It is fed at one end. Here only we are feeding the voltage and we are taking so many number of loads here. So the current values may, based on the machine or motor we are using, the current may be varied. That is, it may be I1, I2, I3, I4 like that. Since it is a concentrated loading, it is not necessary all the current values must be same, and also this distance must not be same. It is not necessary because it is a concentrated loading. That is at that is this distance AC is not equal to CD, not equal to CD is not equal to, it is not necessary. That's all. It is fed at one end. And the next one is DC distributor fed at one end for uniform loading. That is the second category. That is, it is a DC distributor fed at one end and then uniform loading. So this is the second category. That is, we have to tap the current at regular intervals and the current value must also be same. For example, if you are taking current value as 2 ampere per meter, for that means for every 1 meter length you have to tap the current of 2 amperes. That is called as uniform loading. And the next one is DC distributor fed at both the ends with concentrated loading. That is, if you are having a DC distributor AB and you can take so many number of load points, the current value will be different and the distance will not be equal. It is called as DC distributor fed at both ends. That is what it implies means, here you will have the one generation point will be connected here, and then here you may have the another generating station may be connected here. So that only you will have the voltage V1 here, and here you will have the voltage V2, and it will be distributed to the, and the voltage will be current will be flowing here. And then the current value may be different, you can take so many number of points. And the next one is the same thing fed at both the ends, but it is a uniform loading. That is, this circular half circle represents, it is a uniform loading. That is, current value is I ampere per meter. Already I told, if you are having a 2 ampere per meter means every per meter length you have to tap the 2 amperes current from the distributor. So we have to represent like this. And DC distributor fed at the center, that is at the center we are giving the voltage, that is generating section will be connected here, and it will distribute the current or voltage here. So it will reach your distributor A and then B. Here you can tap the voltages. Okay, so if the current reaches here, it will follow the two paths. It may flow from right to left, or and then from here from left to right also. And the next one is ring main distributor. This is the last one, ring main distributors. So if it is a ring main distributor, it is not necessary it has to form a circle. It must follow a closed path, that's all. So here for our understanding we are drawing a circle. So ABCD is a distributor, and here the important thing is we can connect so many number of feeders, we can connect so many number of load points also. Previously we said only one feeding point, and the next we said that fed at both the ends. Here you may have so many number of feeding points, and also you can connect so many number of load points. It may be a concentrated loading or it may be a uniform loading. For example, you take this one. This is a ring main distributor, DC ring main distributor, and here we are feeding the voltage of 230 volts at point A. So here for calculating IA only, they are giving the current direction in the clockwise direction. But based on the voltages and the current values here, that is based on the load here, the current will reverse at one point. So there are some calculations are there. We have to calculate after that. So if you are having the feeding point here, this current is IA. When it reaches the node B, the current load connected here is 10 amps. 10 amps will taken out. So if you are applying the KCL, that is your Kirchhoff's current law. So what is your Kirchhoff's current law? Sum of incoming current equal to sum of outgoing currents, or algebraic sum equal to 0. That is IA, this current is towards the node, so it is plus, and if it is 10 amps outside means it is minus 10 amps, and automatically this will become IA minus 10. Similarly, we have to use and we have to calculate sigma I into R equal to 0. We can find out the IA value. For example, it may be 30 means, if your IA value means 30 means 30 minus 70, what will come? Minus 40. What it implies? We assume the clockwise direction, but the current is flowing in the counterclockwise direction, that is from A to E. So you have to reverse it, and here also you have to reverse it, because here also 30 minus 40 minus 10 amps current will flow from E to D. Okay, that's all. And DC ring main distributor, for example, I told you can connect so many number of feeders here, that is substations here, generating stations here, like that, and we can take so many number of load points, and you can use the transformers also. Based on the consumer side, we have to use the transformers, and with the interconnection means we have to connect any 2 points like that. B and D are connected here, and for connecting the interconnector also there is some procedure. That is, we have to calculate the minimum potential point. At the point at the point D, if the potential is very minimum means, what we have to do means, you have to connect one more distributor from D to E or from D to B, like that. So that is, we are managing the voltage, because if it follows, so many number of kilometers means automatically it is far away from the feeding point. So automatically this will become a minimum potential point. So if you are tapping the 30 amps means it cannot able to supply. So for that, what we are doing, we are connecting a interconnector. That's all about the distribution systems. Let us see the gate questions. Gate 2022. If only 5% of the supplied power to a cable reaches the output terminal, the power loss in the cable in decibel is. So we know very well, and if you want to calculate the power loss in decibel means, you have to take the power loss, not the power. So what is the power loss they had given? They had given, if you are having a 100 means, you have to subtract the 5%. So it is 95 by 5, and they are asking in decibels. So we have to take the 10 log. So this is where if you are putting in the calculator, you will get the value as 12.78. But in brackets they are given round off to the nearest integer. So we have to round off to round up, because it is 0.7, it is greater than 5 means you have to take it as round up, that is 13. You have to fill it here. And the next question is gate 2014. A DC distributor. So this is where DC distributor of 1 kilometer length. This total length is 1 kilometer, having a resistance but negligible reactance. This is also very important. So if you are having a resistance and also reactance means, you have to use the impedance, not the resistance. Impedance means resistance plus or minus Jx, that is reactance. Here the negligible reactance means you can omit the imaginary part, only the resistance you have to take. Is fed from both the ends. So you have to draw two feeding points like that. By 400 volt, what is the voltage here? Here also 400, here also 400, and 50 hertz. Here also 50 hertz, here also 50 hertz. So it comes under AC distributor fed at both the ends. Since the current are not same, it is a concentrated loading, not a uniform loading. Okay ba? And both the voltage sources S1 and S2 are in phase. So in phase and out of phase is also very important in AC. So in AC the power factor is important and the phase is important and then the frequency is important. These three are important things. Why it is important means if you are taking a AC means voltage and current waveforms are very important because it has to follow a sine waveform. V is equal to Vm sin omega t, I is equal to Im sin omega t plus or minus some phi value. So based on the load it will vary. If you are taking voltage and current are in phase means whenever the voltage waveform starts, your current waveform also starts. Whenever the voltage reaches the positive peak, your current will also reach the positive peak. Whenever the voltage again reaches 0, your current value will also reach 0. The same procedure will be followed out. If it is like that, it is called as in phase. If it is out of phase means you have to calculate the phase angle. That is angle between the voltage and current is called as phase angle. Why we are calculating the angle between voltage and current means it is important for the power factor. Power factor plays a major role in the AC circuits. It is not in DC, it will be AC only where voltage and current will not be in phase because of the presence of inductive and capacitive reactance. It may lag or it may lead. If it is a inductive load means it will lag, if it is a capacitive load means it will lead. That is current will lead the voltage. So it is important, but in this case it is both are in phase. The feeder supplies a concentrated loads of unity power factor. Here they are given it is a unity power factor. What is a unity power factor? Power factor is nothing but cosine of the phase angle, that is voltage and current. The angle between voltage and current is called as phase angle and the cosine of the phase angle is called as power factor. That power factor may be of unity power factor, lagging power factor or leading power factor. In this case they are given it is a unity power factor. Unity means 1. When it will be 1, both are in phase. That is your phi value equal to 0, cos 0 will become 1. So it is a unity power factor as shown in the figure. So this diagram is given in the question itself. The contributions of S1 and S2 in 100 amps. Current supplied at the location P respectively. What we have to find out? We have to find out the current supplied by the S1 to the point P and also current supplied by the point substation S2 to the point P. That is the question they are asking. So this S1 is a substation, this S2 is a substation. You are having so many number of loads. Here 3 loads are there, 200 amps, 100 amps and then 200 amps. And the distances directly they are given from the S1 400 meters, from here to here 200, here to here 200, here to here 200. And we have to add it 400 plus 400 plus 200, 1000 meters. It is equal to 1 kilometer. In the question also they are given it is a 1 kilometer. So in the first line itself they are given it is a 1 kilometer. So we matched all the things. Next we have to do the calculations. So first what we have to do means we have to form a tabular column. It will be easy for us. First we have to represent the sections. Next current in each section. Next resistance of each section and finally voltage drop. So in this how many sections we are having? I had given the name A, B, C, D and all. You can give as your wish. So I had given the name as A and then B distributor. In between C, D, E are the 3 load points. C, D, E are the 3 load points. This is a feeding point A and this is a feeding point B. I had given like that. You can change the notation also. Next, what are the various sections now? From A to C, one section, C to D, D to E, E to B. So there are 4 sections are there. So note down the sections and then the current in each section. We have to assume the current first because the current in loads only they are given. In the distributor we have to note down. These are the load currents. And we have to note down on the distributor, they are not given. So the total current supplied by S1 I am taking it as I. You can take from the B, say B also, it is your wish, and the current is I. When the current reaches the point C, what is the current we are typing here? 200. So in this section CD, what is the remaining current? I minus 200 by applying the Kirchhoff's current law, I minus 200. Next when it reaches the point D, again we are tapping the 100 amps. So 200 minus 200 minus 100 minus 300. So I minus 300. When it reaches the point E, again we are tapping 200 amps. So minus 300 minus 200 minus 500 we will get. So in this section the IB is I minus 500. So these are the current in each section. And the next one we have to calculate the resistance. So how to calculate the resistance? In the problem what they had given, they didn't mention the resistance. We have to calculate. How to calculate? We are assuming resistance per 1 kilometer length, we are taking it as R. So that is R divided by 1000 ohm per meter length. So R by 1000 for 1 meter length. So for the section AC, what is the length they are given? 400. So you have to multiply for 400 meter lengths. So for 1000 meter, I am having the resistance of R, means for 400 meter, I have to multiply by 100. So what is the value I am getting here? And the next one is for the section CD. C to D, what is the distance? 200. So I have to multiply by 200. Next from D to E, what is the distance? Again 200. So the same answer only I will get. Next from E to B, again it is also 200. I will get the same answer. This is your third column. First one is section, current in each section and the resistance of each section. And finally we have to calculate the voltage drop. What is the voltage drop formula? I into R. Always the voltage drop formula is I into R. So I into this R value. You have to just multiply these two columns. So we will get the answer as this one. And the next thing, since they are given S1 equal to S2 means sigma IR equal to 0 because it forms a closed path. So sigma IR value equal to 0. For example, here it is a 400, here it is also 400 means it will supply the current in this direction. This substation will supply the current in this direction. Both are in opposite direction. So what it will do? 400 minus 400, you will get 0. It is equal to what? That is your I into R. Sigma I into R. So what we have to do? Sigma I into R equal to 0. How to find out the sigma I into R? Already we found the voltage drop. You have to add it. That's all. This symbol represents it is a summation. So you have to add it and equate it to 0. If you are equating it to 0 means what we are getting? This equation into R value equal to 0 means R value is not equal to 0 because it is a resistor. If you are taking any wire or anything else, it will have some resistance value, that is it will oppose the flow of current. So R value should not be equal to 0. So the remaining portion is also must be equal to 0. So equate it to 0 and find out the current value. Now note down the current in the same tabular column. What is the current value I got? 200. Substitute the I value here. 200. First one is 200. From A to C the current value is 200. Next from C to D, what is the current? I minus 200. 200 minus 200, 0. So in the section CD there is no flow of current. And the next one is D to E, 200 minus 300 minus 100. So what it represents? I have to change the direction. Previously I had notation is from D to E. Now I have to change the direction from E to D and the current is 100 amps. And the next one, 200 minus 500, I will get minus 300. So minus 300, here I have to note it down. So if the 300 is coming here, 200 is tapped off. So the remaining current is 100 amps. Here 200 minus 200, it becomes 0. So no current is supplied by the S1 at the point P, but 100 ampere current is supplied by the substation 2 alone. That is the answer. Let us see the next question, GATE 2008. Single line diagram of a 4-bus single source distribution system is shown below. There are 4 branches, E1, E2, E3 and then E4 have equal impedance. Impedance is important in AC circuits. Impedance means impedance Z is equal to R plus or minus JX. You are having the equal impedance. So equal impedance, and the next one is the load current values are indicated in the figure. So this figure is given in the question itself. This is your figure and are in per unit system. Distribution policy requires a radial system operation with minimum loss. So you have to neglect, you have to avoid one branch here such that your loss must be minimum, because if you are removing one section means you are doing saving of copper. So if copper is saved means my cost will be saved. So that is the main thing. So I have to eliminate E1 or E2 or E3 or E4. That is, I have to remove it from the diagram, because for example if you are taking this one, this load means if there is no E1s means the current will flow like this. So it will also supply all the loads. Or otherwise I am eliminating the E2 means the current will flow like this, it will supply the loads. Similarly I am eliminating the E4 means the current will be supplied for this load here and for this and this load it will be here. here. And if I am eliminating the E3 section means the current will be in two branches. In E1 it will be for the first load it will be here, and for the second and third load it will be distributed like this. So anyhow we will have the distribution of current for all the loads. So I have to eliminate any one of this section in order to save the copper, in order to save the money. So the minimum loss must be there. That is the important factor they are given. Let us see how to solve it. If I am eliminating the E1, I have to calculate the loss. What is the loss formula? I square R. You know very well, I square R. So what is the current value they had given here? 8 amperes. The current value here they are given is 8 amperes. 5 ampere has been tapped off. So current has to flow in this path only. So 8 minus 5, 3 ampere will come here. This current is 2 amperes. So 3 minus 2, 1 ampere will be going here. So this is the thing. So what is the formula for I square? What is the formula for power loss? I square R. So I can add it all the things because the impedance value are same. So it is not necessary to worry about the R value. Okay. So I square R means 8 square plus 3 square plus 1 square. What is the answer I am getting? 74 into R. Similarly, the next one is E2 has been opened. So if you are opening this, the diagram will be like this. So current will be flowing here, here and then here. So what is this current? 8 amperes. This current value we are tapping off 1 ampere. So 8 minus 1 we will get the 7 amps. That is just we have to use the Kirchhoff's current law. That's all. This is the incoming current, this is the outgoing current, this is also outgoing current. Sum of outgoing current must be equal to 8. That is 1 plus 7 equal to 8. That is the thing. Similarly, this is 7 amperes, 2 ampere I am tapping off. So the 5 ampere will current flow here. So now what is the I square R loss? 8 square plus 7 square plus 5 square. That is I am getting 138. When compared with this is having more loss. So it is not advisable. Next take the third one. If E3 is opened, this conductor has been removed means I am getting 1 ampere here and then 7 ampere I am taking off 5 amperes here. So 7 minus 5, 2 amperes will be flowing here. I square R loss will be 1 square plus 7 square plus 2 square into R. I am getting 54 R. When compared with the first and the second one, it is having the minimum one. Loss is minimum. Let us see the last option. That is, if the section E4 is opened, if the portion is opened means this is 3 amperes, this is 5 ampere. So this 3 ampere, 1 ampere tapped off. So 3 minus 1, 2 amperes. This 2 ampere will go through this load. That's all. Now what is the I square R loss? 3 square plus 2 square plus 5 square into R value. I am getting 38 R. When comparing all this, the power loss is very less in this only. So I have to open the E4 to reduce the power loss. And the next problem is DC distribution system shown in figure with a load currents as marked. Load current. So 10 amps, 20 amps, 30 amps, 15 amps are they are given directly. The two ends of the feeder are fed by the voltage sources such that Vp minus Vq equal to 3. That is, it is a DC distributor fed at both the ends and then concentrated loading. The voltage Vp minus Vq equal to 3. They are not given. It may be 200 and then it may be 197 like that. So if you are subtracting it, we will get the 3 volt. The value of the voltage Vp for a minimum voltage of 220. That is, I have to get the voltage of at point P, the voltage is 220 along the feeder line. Let us see how to solve the problem. So the same diagram only I have taken 10, 20, 30, 15. 10, 20, 30, 15 and the feeding points are P and Q. In between we are having R and S. P and Q and then R and S. That's all. So 10. Similarly, we have to do the tabular column. How many sections are there? Current in each section, resistance of each section and the voltage drop. So how to find out the sections from P to R, R to S, S to Q. So there are 3 sections. So in the 3 sections, what is the current? If I am taking the current values initially I means the current value I am taking the first load as 10 amps. So I minus 10. Next I am taking 20 amps. So I minus 30. Next I am taking 30 amps. So 30 minus 30 minus 30 minus 60 amps. This is the thing. Next one, the resistance values. Resistance in each section in the diagram itself they are given 0.1, 0.15 and then 0.2. 0.1, 0.15 and then 0.2. Next voltage drop formula is I into R. This column into this column I will get this. And the next thing is sigma IR equal to 0 if both the voltages are same. But in this problem they are given sigma IR equal to 3 volt. So in this problem they are given it is a 3 volt. If both the voltages are same means, and if it is feeding means the current will be in opposite direction, we can substitute it is equal to 0. But in the problem itself they are given Vp minus Vq equal to 3 volt. So sigma IR equal to 3 here. So add all the voltage drop and equate it to 3 and find out the current value. I am getting 45.56. Now substitute the current value in the diagram or other substitute in your tabular column. So what we are getting 45.56, 35/15. Like that only. So S is the minimum potential point. If you are subtracting 15 minus 30, I will get the negative direction of the current. The current is reversed. So S is at the minimum potential. So it is not necessary to find the remaining things because it is time consuming. So we have to avoid that. What is the question they are asking? We have to do at that point only. And they are asking the Vp. So at this portion it is okay. So what is our Vp? 220 volt is given, plus you have to add all the voltage drop. So the Vp is given as 225.89. So this is the potential at point P. That's all. Thank you. We will see it in the next class.